Hello everyone, my name is Nathalie Rauschmeier and I'm working as an applied scientist at AWS. Welcome to my webinar. Today you're going to learn how to do anomaly detection with Amazon SageMaker, AWS DeepLens and AWS IOT Grass. Let's first start with a quick overview of nowadays agenda. In the first part of the webinar, I will show you some general use cases for anomaly detection. In the second part of my webinar, I will introduce a special type of deep neural networks called autoencoders that can be used for anomaly detection. Then in the third part, we will focus on anomaly detection at the edge. And last but not least, I will give a demo through Amazon SageMaker, AWS IoT Grass, and show you how you can deploy your deep learning models to the edge. So what is anomaly detection? In very general terms, we can say anomaly detection is about finding the data items that do not follow the majority of your training dataset. So anomaly detection is also sometimes called outlier detection. So let's assume you have a training dataset that follows a Gaussian distribution, and now your goal is to find these little outliers here that are basically not following your distribution of training data. There are different use cases for anomaly detection. When we think, for instance, about time series, then there are use cases like predictive maintenance. Predictive maintenance is all about trying to predict whether a machine is working normally or whether there is some sort of anomaly that may indicate that the machine may fail in the near future. We also find use cases like fraud detection. So think about your credit card and you perform credit card transactions. So if someone stole your credit card details and will now perform a transaction that is very, very far in a geographical different location, then very likely this will trigger your bank to block your credit card. We also find anomaly detection in intrusion detection. Imagine a network and you have a lot of users that are logging into your network. And now you try to find if there is a malicious attacker that is trying to intrude your network. There are also plenty of use cases for images and video. So for instance, medical imaging. When we go to the doctor may perform an X-ray of our body, and then the doctor will try to data mine whether everything looks normal or not. If it does not, it may indicate that we are sick. We also find anomaly detection in manufacturing. So think about use cases like defect detection. I took here some images from a paper where they are doing defect detections in tissues. So these little blobs here are basically anomalies and they try to find them with deep neural networks. While for us human beings, it can be difficult to find these small blobs. For a deep neural network, it's kind of very easy. We also find use cases like CCTV. Nowadays, we find web cameras in many public places, in buses, and typically there are some people looking at a video stream 24/7 to identify whether everything is normal or whether there's somewhere an accident or a traffic jam. And we also have use cases like anti-counterfeit. So imagine you have your own brand and you are selling some items and you want to make sure that there is not a malicious seller that is trying to use your brand logo to sell his own items. So what are the challenges in anomaly detection? We find many use cases in IoT applications, for instance, like predictive maintenance or CCTV, where a lot of data is generated. But very often we only have few or no labels at all. So if we train deep learning models like image classification models, we typically need a lot of training data and a lot of labels. But if we are not having enough labels available, then we have to use different techniques for training the model. Another challenge is classifying anomalies. It can be sometimes really challenging to distinguish between normal and not normal. So let's think about a CCTV use case where we are monitoring a pedestrian zone. We all can clearly agree that if we see now a car driving through a pedestrian zone, that would be clearly an anomaly. But what about a person on a skateboard? So how can we tackle those challenges? We can use deep neural networks that can easily identify hidden patterns in our dataset and can learn the underlying features in our dataset. If we only have very few labels available, that means we have to go for unsupervised learning approach. That means we do not provide any labels to our deep neural network, but rather just the data as it is, and it will basically learn what is normal, and then during inference can infer whether the given input looks like the training data or not. If you have to deal with lots of data, typically we want to perform real-time inference. So when we think about IoT applications, then typically we want to deploy these models to the edge where the data is generated. So let's switch to the second part. What are autoencoders? Autoencoders are a special type of deep neural networks that consist of two parts. We have first an encoder that basically learns the image features. So we take the input and we have now multiple network layers. The more layers we have, the more complex features we can learn. The encoder downsamples the input and creates a compressed representation of the input data. The second part in the autoencoder is the decoder. The decoder takes the output of the encoder and it tries to reconstruct what the original input was. And that may sound kind of trivial because what the autoencoder in the end does is trying to learn an identity function. That means we try to reconstruct on the decoder side the input from into the encoder. And that is also why it's called autoencoder. However, the autoencoder consists of a bottleneck layer, and that forces our autoencoder to learn a compressed representation of the input data and to basically only learn the most meaningful features in our training dataset. So here's an example how the training of an autoencoder on the MNIST dataset would look like. MNIST dataset is a common dataset used in deep learning, which consists of the digits 0 to 9. And what we see is when we feed in now this image of the number 7, we see that in the beginning, the autoencoder will not reconstruct the original number 7 very well, but already after a few iterations, it's doing a pretty good job. So how can we use this mechanism now? An autoencoder, once it's trained on a certain task, it will not be able to reconstruct what it has not seen during training. So I have shown you an autoencoder that was trained on MNIST digit dataset. And now I will take the very same autoencoder and during inference, I will show some images of characters. What will happen is that the autoencoder will reconstruct something, but not very well, because it has never seen characters during training, so it will not be able to reconstruct them very well. And we can use this mechanism now to identify whether the given input into the autoencoder contains anomalies or not. How we do that? We take now our input image here on the left side, we take the reconstructed output image and we create the difference between them, also called residual map. If we see a lot of high reconstruction errors in this difference image, we can conclude that the input contained an anomaly. And if we do now the same for the digit dataset, we see that we only have very small reconstruction errors because the autoencoder knows how to reconstruct digits, but it does not know how to reconstruct characters. So now I would like to show you how you can implement an autoencoder model with the deep learning framework MXNet. MXNet is a deep learning framework that supports hybrid programming. That means we can start defining our deep learning model in an imperative way that allows us to more easily debug the model. And once the model is training fine, we can hybridize it and get a performance speed up. In order to be able to hybridize it, we have to inherit from the hybrid block class. So the first part in the model is the encoder. What we do here, I define here a hybrid sequential where I'm basically stacking all my encoder layers together. I have here now different channel outputs for my convolutional layer. So the channel output is 16, 32, 64, 128, and 256. And the convolutional layer is followed by a max pooling layer. So the sequence of these layers are learning now the underlying features in my input images. Afterwards, I define another hybrid sequential where I'm stacking now the layers of the decoder. The decoder basically reverses all the operations done by the encoder. That means my max pooling becomes now an upsampling layer. I define here a hybrid lambda and here the upsampling. My two-dimensional convolution becomes now a deconvolution, a convolution transpose. And then in the hybrid block, I also have to define a hybrid forward function that basically will define what has to happen during the forward pass. And I'm passing here now my data through the encoder followed by the decoder. This type of convolutional autoencoder, I trained it on the UCSD Anomaly Detection Dataset, which is a publicly available dataset provided by the University of San Diego. What they did, they mounted a web camera on the university building overlooking a pedestrian zone. During the training, only images of pedestrians will be visible. And during inference, so during testing, there are certain anomalies. And so the goal is that the model picks up those anomalies. So what we see here is that is the original test image as input into the trained convolutional autoencoder. That is the output of the autoencoder. And we see that it does not reconstruct too well the human beings. And that is with intention because we have a bottleneck layer that forces our autoencoder to just learn a compressed representation. And then here, that is the residual map. That is basically the output of the autoencoder minus the input. And what we see is that the objects which it has not seen during the training, like the golf cart, is causing very high reconstruction errors. And what I do in this plot here, I'm basically trying to find now the pixels with high reconstruction error. But before that, I'm applying a convolution on the residual map because it may happen that there is a certain pixel that is causing a very high reconstruction error due to some noise. And the convolution has the effect that we will only annotate pixels if the neighboring pixels also have high reconstruction errors. And by doing that, we are able to minimize the noise and the false positives. And I'm annotating here basically the pixels with high reconstruction error. So we see that the golf cart is actually nicely detected. So there's one limitation of the convolutional autoencoder, and that is it does not take the sequence of images into account. And that can be a problem because we may not be necessarily just interested in an anomaly in form of an object, but maybe also in form of a movement. So let's assume a person on a skateboard. A person on a skateboard may not be so much different from a normal pedestrian, but it may move much faster. So how can we detect that? We can adjust the convolutional autoencoder by, instead of taking now a randomly sampled set of images, it takes now a randomly sampled set of sequence of images. So in this case, we try to make sure that our training data set consists of sequences of 5 time steps, and we randomly sample from these sequences. Then the autoencoder still has these convolutional and deconvolutional layers, but the bottleneck layer would now consist of a temporal encoder and decoder. You can use here, for instance, convolutional LSTM cells. These are special types of LSTM cells, and they have proven to be effective for video processing. And by doing that, your autoencoder can now also learn what is normal in terms of sequence of images, so in terms of movement, whether there is an anomaly or not. So when we think about use cases where we want to generate our own training data, then we also have to think about how to pre-process the data. So let's assume you have a web camera and you generate some image data. So what will happen is that on one day it might be very sunny, on the next day it's very rainy. So there are a lot of conditions that will influence the image quality, and that may of course also influence the model training. So what we can do is histogram equalizing. What does this mean? So on the left side, this is the original input image, and we see now when we look at the distribution of grayscale values, we see that they start at roughly 50 and they go to roughly 200. So the spectrum is from 0 to 255, but in that left image, we are actually not fully exploring the full range. Histogram equalizing, what it does, it makes sure that we fully explore the full scale from 0 to 255. And when we plot the cumulative distribution function, which is indicated here in blue, we will see that it's a linear line. And the effect of histogram equalizing is that we can increase the contrast of our input images. And that also means the weather effects are kind of minimized and the model training will improve. Another important aspect is the loss function. So when we train an autoencoder, then the autoencoder has an input and it produces an output, and it has to compare the similarity between input and output. So typically what people use in deep learning is the L2 loss, or also called mean squared error. But there is an issue with this loss function. L2 loss assumes that our pixels are independent. That means it will take the first pixel value in my input image and compare it with the intensity value of my first pixel in the output image. If I get a value that is close to 1, it means images are dissimilar. If I get a value close to 0, it means they are similar. So here I added 3 images. On the left side, this is my original input image. In the middle, this is an image where I slightly modify the contrast, so my image loses some information, like for instance, we can't see here that object in the lake anymore. And in the third image, I put a filter on top of it so that the image is very blurry. If I compute the L2 loss, or also called MSE, I get in both cases a value very close to 0. So here it's 0.012 and here it's 0.014. That means for the L2 loss, both images are equally similar to the original input image. However, that is not how we as human beings would perceive similarity, because when we look at that image here on the right side, we would all agree that that should be very dissimilar. So we can customize the loss function. There is something called structural similarity index, SSIM. It takes the structure, the luminance, and the contrast of neighboring pixels into account. So it does not just focus on the intensity value of a single pixel, but it will also take into account the neighboring pixels. If we get a value that is close to 0, it means images are dissimilar. If we get a value close to 1, it means they are similar. So it's the opposite, like in the L2 loss. And what we see now is that in the case of the image here in the middle, we get an SSIM value of 0.5. That means the images are not too similar, but also not too dissimilar. We are somewhere in between. And it actually makes sense, because by changing the contrast, we lost some information in the image. But more important is that in the case of the image here on the right, we get now a value of 0.05. That means that image is very dissimilar to the original input image. And that is how we as humans would also perceive similarity here. So using a customized loss function like SSIM can help you to improve the autoencoder training if you want to detect anomalies that are kind of very fine-grained and difficult to detect. So now I would like to switch to anomaly detection at the edge. So we can use devices like AWS Deep Lens. Deep Lens is a deep learning enabled video camera for developers. It provides over 100 gigaflops of compute power, so that allows you to do predictions in real time on the device itself. And so how can we use now AWS services and Deep Lens together? So when we have our edge device like Deep Lens, then this device is running in a local network. And we can connect it to the AWS cloud via AWS IOT Grass. What we have to do, we have to install certificates on the edge device and register those certificates in the IOT Grass console. Once we deploy, the edge device can securely communicate with IOT Grass, and we can now also deploy Lambda functions. So what we do is we can define subscriptions and topics that basically allow us to communicate with the edge device. We can use protocols like MQTT, but also HTTPS. And if we send now from the AWS IoT console a message under the topic get data in this case, we can connect an action to it. And in my case, I defined a Lambda function get data that basically once I receive this message from the AWS IoT console, that means my Lambda function will be executed on the Deep Lens device. This Lambda function will now generate some images and upload them to Amazon S3. Once I have training data on Amazon S3, I can go to Amazon SageMaker and start training a convolutional autoencoder model. Once the model is trained, SageMaker will automatically upload the model artifacts to Amazon S3. The next step is to connect these model files with IoT Grass. That happens via the machine learning resource. If I deploy now again my Grass deployment, what happens is it will automatically download the MXNet convolutional autoencoder model onto the edge device. But now I need another Lambda function because I need a Lambda function that does something with the model. So I defined here a Lambda function called Inference that is now registered under a different topic. So if I send a message under the topic Inference, it will trigger the Lambda function Inference, which will then get some data from the Deep Lens device and perform inference on the MXNet model. And now we could go even a step further where we connect this Lambda function with some CloudWatch alarms. So if my model detects too many anomalies, then maybe it should somehow send an alarm in CloudWatch. So now let's have a look on the AWS console and how we define the training and deploy the model. So this is the Amazon SageMaker Console. So we can go now to our notebook instance. I have here my anomaly detection notebook. And what we are doing here now is we are trying to detect rotten strawberries. So what I do is the goal is to train an autoencoder model that will now be trained on normal strawberries. And during inference, it has to distinguish whether my strawberry is normal or whether it's rotten. So the first thing we are going to do is we define the SageMaker session and get an execution role. We have to do that because SageMaker later on will spin up automatically a training instance for us, so it needs permission to do that. Then we have to define an MXNet Estimator. The MXNet Estimator takes an entry point script. I will show that to you afterwards. Then it takes the role. We define here the instance type on which we want to train the autoencoder model. Typically, you would want to train on a GPU instance, so I selected here the P2 instance. We also indicate here the instance count. So since I'm not doing parallel or distributed training, I choose here an instance count of 1. And then we can indicate a dictionary of hyperparameters. This is useful if you want to do automatic model tuning later on with Amazon SageMaker, because it can then automatically adjust these hyperparameters to find the best set of hyperparameters. So once we define the MXNet Estimator, the next thing we are going to do is we will call MXNet Estimator.fit. That will basically execute the training. We indicate here now the S3 path to the data where the images of good strawberries are located. And what will happen, we will get now a lot of output here. So first, SageMaker will create the training instance. Then it will automatically download the training data into this instance and then start the training. Let's have a look on the training script. So as I've shown before, in the MXNet Estimator, we indicated a train.py file. Let's have a look into this file. What we do here, first we define the convolutional autoencoder model that is slightly different than to the one I have shown you in the presentation, but has the same concept, encoder and decoder. Then we define here the training loop. SageMaker expects that the file follows a certain format, so we have to provide a train function. And in the train function, what we do, we can now access the files that are automatically downloaded by SageMaker into the training instance. And there are environment variables that basically define the path to the data. So this one is now SM_channel_train is the path to the training data. We pre-process them and then we define the data loader. And then here we basically start training the model. Once the model is trained, we have to save the model. We choose here now the environment variable model_dir. And that will basically save the model, and SageMaker will pick up the model from there to automatically upload it to Amazon S3. So now that the model is trained, we can do the deployment. What we do is we use now the MXNet Estimator and just call deploy. So that is basically a one-click deployment. We indicate the instance type we want to run on. In this case, I chose a P2 instance, but typically you would probably want to run on a CPU optimized instance if you are not having large workloads. And then you indicate here the instance count. Once this is deployed, you can actually now go to your SageMaker console and check the endpoint. So this is the deployed endpoint. And we can click on it. There are also, go to the log files to see which kind of incoming requests it has received. We can also look at the statistics to see, okay, what was the memory utilization, CPU utilization. So we get a lot of information here. And now, since the endpoint is deployed, now I can perform inference. That means my trained model is running in the endpoint, and I can now send requests from my notebook instance to the endpoint. So in order to do so, SageMaker needs some more functions in the train.py. We define here a model_fn that basically creates the convolutional autoencoder. It hybridizes the model and then loads the parameters. And then we need a transform_fn function that will basically take the incoming request and pre-process it. So per default, the incoming request is encoded as a JSON string. So we have to load this data into a NumPy array, and then we have to pre-process it. And here we do the inference. Once we have the result from the autoencoder, we convert it back into a JSON string and send it back. So what I'm doing here, this predictor.predict, I will now send some images to the endpoint, and get the autoencoder output back. And then I can do some processing here. So that is my input image that I'm loading from my local notebook instance. That is the result I'm getting from the endpoint. And now I can build a residual map and see, okay, where are the anomalies? And as we see, it's now nicely detecting the rotten parts here that are annotated as blue pixels. But now let's think about a use case where we actually don't want to deploy to the cloud, but rather to the edge. And that's where we can now go to IOT Grass. So if you log into your Grass console, you will see a Grass group, and your edge device is now listed as a core within the group. And as I said before, we have to define subscriptions that we can connect to a Lambda function. So we define here the source and the target and the topic. So as I said before, I had two Lambda functions, get data and inference. And they basically, for each of them, I have a different subscription. We can now look also at these Lambda functions. So we can go to the Lambda Management Console. And we see here now the list of Lambda functions available. So let's have a look on the get data. What I'm doing here is basically, I have a little Python script that is basically getting deployed to the edge device. And since I'm using DeepLens, I have to use the module here, AWS CAM, that is pre-installed on the DeepLens device. And basically, I have a Lambda handler where I'm just reading frames from the DeepLens. I pre-process them. And then in the end, I upload everything to Amazon S3. And how does this look like? So how can we trigger this now? You can go to test, and then you basically define here your topic like get data. You subscribe to it, and then you can send a message. And once you did that, that will basically execute the Lambda function on the DeepLens device and start uploading data. And for defining the machine learning resource, what we have to do is we have to go to resources, and then we can here say add a machine learning resource. We have then the option to either upload a model to S3 and just indicate the path to S3, or we take a model trained in SageMaker. So if you go and select a training job, you get the full list of models that have been that you have been training. And so we can just select this model and attach it as a machine learning resource. And then what will happen is if we go now to deployments and we call deploy, basically these Lambda functions and the autoencoder model will get downloaded on the edge device. And then we can perform the test and execute these Lambda functions. So when we talk about edge deployment, then it's also important to mention SageMaker Neo. SageMaker Neo is a feature of Amazon SageMaker that allows you to compile your model for a specific hardware target and to get the most optimal performance out of it. What you have to do is you go to the SageMaker Console and then Compilation Jobs. You can now create a compilation job where you indicate the S3 path of where your model artifacts are located. You indicate here the input size of your data. So in my case, the autoencoder model would take images in the form of batch size, and then we would have the color channel, width and height, and it would be 128 width and 128 pixels height, and that is something we could indicate here. Then we have to indicate the framework we have trained a model in, and then we indicate where the optimized model should be stored, and we can now choose the hardware target for which we want to optimize this model. In our case, it would be the DeepLens device. And so what does SageMaker exactly do? So when we think about deep learning, then we have multiple deep learning frameworks like MXNet, TensorFlow, PyTorch, Onyx. And now you want to deploy your model to a specific hardware target, and you want to run it as fast as possible. So when we think about edge deployment, then the issue is that you may face a lot of resource requirements and constraints in terms of memory and so on. And it can be a very tedious and iterative process to optimize your model to fit into an edge device. And SageMaker Neo basically allows you to automate this process. We just indicate that we have here an MXNet model and that we want to run on a certain edge device. So it supports Intel CPUs, NVIDIA GPUs, Qualcomm, ARM, and other edge devices. And it will basically take into consideration the hardware configuration of the specific hardware target and optimize the model for inference. The kind of optimization SageMaker Neo will apply are happening on the graph and the tensor level. When we think about deep learning models, then deep learning models are a computational graph. And it's a sequence of operators that get executed. And what SageMaker Neo will do, it will perform pruning. That means there are certain operators in our model that we need for training, but we don't need during inference. A good example is, for instance, dropout. We need dropouts to regularize the training, but we don't use it during inference. So that's something that is going to be removed. Then the next optimization is the layout transform. When you load an image with OpenCV, then typically your image will be loaded with height, width, and color channel. And in deep learning, we also have another dimension, the batch size n. But for accessing caches, it's much more efficient to have the layout, batch size, color channel, height, and width. So to have the color channel in the second dimension. And that's something SageMaker Neo will do for us to improve performance. Another important optimization is operator fusion. So every time you're going to execute an operator on the GPU, it will require a constant kernel launch time. And if the time to execute your operator is small, then this constant kernel launch time can create a lot of overhead. What you do in operator fusion is you try to minimize this launch time by fusing operators together. So in the case of here, you have 3 separate operators, and for each of them, you have to also add the launch time. And now you fuse one of them, so you only have the launch time 2 times instead of 3 times. Then SageMaker Neo takes also the input size into account, and based on the data input size, it can then data mine the size of the tensors in our computational graph. And it will perform optimizations like tiling that basically will improve the spatial and temporal access patterns. So it will improve cache performance. And it will also apply vectorization. So instead of having a summation 4 times here, it will just do the operation once on 4 data items in parallel. That is basically single instruction, multiple data, and that can greatly improve performance. So that's it from my side, and now I'm open for questions.